perception team there, working on wide variety of use cases, largely focused on, if I'm correct, autonomous driving. I think you already know him by the introduction to Samadho gave, right, where they're shown as video walking in the robotics lab. Perception team there. Sorry?
Sorry, what did you say?
So Madhav gave a talk in this event, and he showed your video walking
My
in the.
yeah. I had such a good time at Triple IT Hyderabad working with Dr. Madhav and
This meeting is
Sivi.
being recorded.
Yes. So he, of course, did his master's here, Professor Madhav and Jawahar jointly, and he did his PhD afterward at Georgia Tech, Professor Rangalar, who advised Professor Ren. And yeah, so I think quite interesting papers he had already got, and he is going to talk about his recent work, which is a CBCR 2022 accepted paper. I think not yet presented there, I believe, on Panoptic neural field. But it is before he give a brief overview of neural fields and nerve and this kind of recent advancement. So over to you, Abhijit.
Okay, thanks a lot, Avinash, for this nice introduction. Yeah, I mean, this is my first presentation at Triple IT Hyderabad after I don't know, almost 10 years. So yeah, I'm very, very happy to be there. So you guys can hear me and can see my slides correctly, right? Is that a yes?
Yes, sir, we can see.
Yeah. Awesome. Okay, so yeah, as Avinash was saying, I am currently at Google Research in the perception team. So it's like a big team. So it's like basically the team which does a lot of computer vision and also like speech understanding. So, and we work with lots of other teams within Google, like whether it's Waymo, whether it's Geo, and lots of different applications, right? And also within Google, we have a lot of excitement about neural scene representations. So today, that's exactly what I'm going to talk about. So the title of my talk is Neural Scene Representations for 3D Scene Understanding, right? So let's make it interactive. So I don't have a lot of slides. So feel free to stop me at any time, ask any questions, okay? So let me first define what scene understanding, or what at least I mean by scene understanding in this particular talk, right? So what is perception? So perception has been defined like way back in like 1866 as the best guess of what is in the world given some sensor input, right? So you want to use some prior knowledge that you have about your world and some sensor information, and you want to describe what is in the world, right? That's basically kind of the definition of perception. So scene understanding is a very broad field and a broad topic, but you can define it as like extracting a very compact representation of what is in the world, right? And what is a good representation, right? And that question is actually like varies, right? So I think the question, what is a good representation, is not really a good one. The only thing is that there is only a good representation for a particular task, right? So maybe some representation is good for one particular task, it may not be good for something else, right? So in this particular talk, we would be a little bit more interested in kind of 3D detailed semantic level understanding of the world, right? So a very traditional representation for something like this is kind of image level representation. For example, like for every pixel in your image, you want to know whether it's sky, whether it's road, whether it's a human, right? Or you might want to know what is the 2D bounding box extent of an object, right? So kind of image level representation. Of course, you can also want to do something like 3D representation. Sometimes, like for example, if you want to do self-driving cars or you want to do path planning, maybe such 3D representations are much more useful, right? So also like the representation can also change by how exactly the 3D information is stored, whether it's stored like volumetrically, like a grid of values in your world, or it is stored in some sort of meshes, right? So each representation has its pros and cons. Maybe some representation is easier to train if you want to actually have a method that goes from images to this 3D. Maybe something is faster to render, right? So for example, meshes are very fast to render. So if you have a graphics card on your laptop, you can render meshes at, I don't know, at 10,000 frames per second, depending on the number of triangles in that mesh, right? So now the question is that if you have an image, how do you get to something like a 3D representation, which is kind of very useful, right? Like for example, in applications like autonomous driving, robotics, right? One standard way is like you have ground truth data, which are also in 3D, and you actually just take your favorite convolutional neural network and train it in a supervised way, right? You have given images, you are learning to map some neural network that goes from the image representation to your 3D representation. This works extremely well, but of course you need 3D supervision, which is hard to get, right? So how do we want to solve this problem of getting 3D understanding or getting a 3D out of 2D images, but when you don't have 3D supervision, right? And one way to solve this is something, a very traditional approach of solving this is something called analysis by synthesis. So that's the second definition I want to get into, right? So, so imagine you have some world model, like how your 3D representation is, right? If you can, and you have some parameters that is describing how your world is, how your 3D world is, right? And you can sample from this distribution of world, and you can do one thing, which is like if you have this 3D world, you can use computer graphics to render a 2D view of this 3D world, right? And once you have rendered that, you can then compare with some sort of 2D observations you have. Let's say you have a camera image, right? And if you have this entire process differentiable, so that means you have this differentiable rendering engine, you can actually do this in a loop. And in some ways, what you are doing is that you are rendering, so that basically means synthesizing a new view, and you are then comparing. And with this, you can try to find out what parameters of your 3D scene is best describes the observed images, right? So you can think of analysis by synthesis with a 3D scene model is like solving computer vision with inverse graphics. So let me get a little bit more into that. So computer vision is more like given some image 2D data, you want to find out what's the 3D understanding representation of the scene. Whereas graphics is the opposite, right? Like you are given a 3D representation, you want to get an image out of it, right? So you want to use this graphics in the inverted way to solve computer vision, right? And there's a very like kind of old school idea, and lately we are seeing a lot of work. So all the works that I'm going to talk about today, NERF including, is an example of analysis by synthesis, right? And I think we are at a point where we have really good uh, differentiable graphics renderers. And I think we are going to see much more of traditional computer vision being solved by kind of analysis by synthesis kind of way, or you can also say inverse graphics. I think that you can also think of the analysis by synthesis as like kind of a specialization of this class of problems called inverse problems in math. Okay. Okay, so let me just briefly kind of describe what this thing called NERF is, neural radiance field. So I have very brief slide. I'm kind of assuming that at least some of you have seen these things. So if you have not, I would say ask, like, maybe after the talk, you really want to see at least some videos of this particular paper, which kind of does a very good job in explaining what it is, right? So this is an ECCV work with Ben, Pratul, Matt, John Barron, Ravi, and Ren. Out of that, both Ben, Pratul, John are all also in Google in perception. So they are working exclusively on neural radiance fields. So what is neural radiance field, right? So the crux of this paper is actually a scene representation, which is materialized by an MLP, multi-layer perceptron, which takes as input the 3D position, like the XYZ coordinate at any point. And also, if you optionally, you can also take the view direction of a ray, and it outputs the color and density, which is together forms the radiance field at any point. So basically, the reason it is called field because you have this continuous function. So given some position, you want to get the color and density at any point in some bounded volume, right? So once you have that, but okay, let me just first also say how exactly is that multi-layer perceptron. So typically you have um, I don't know, like typical, like around 8 layers of MLP with certain depth, typically around 250. Sorry, uh, the width of the MLP is typically around 256 neurons, and you have typically around 8 layers. That's the standard configuration. Also, maybe the position data, you wanna probably also have some skip connections to make sure the it's especially when if you have the uh, if you have like 8 layers or anything more than 6 or 7 layers, you typically really want to have some skip connections in the style of ResNet, right? Uh, Also the direction information. So basically the main idea of why you want to condition the direction is that sometimes the the color that you observe of a pixel really depends on what direction you're viewing it from, right? So you also want to optionally condition the output color based on the direction. So you can also feed that, right? But the density, you don't want to condition that on the direction because whether a point is kind of occupied or not really does not change whether you see it from top, bottom, side, or left, right? Another important component is this thing called PE, which stands for positional encoding. That's basically kind of mapping the input coordinates and adding some Fourier frequencies to it. I will not go into detail. It's super easy, but what you should take away from this thing is that it's super important. And actually, that's one of the things that makes it work. And which is kind of shown in this particular video on the right, where you have, let's say, an image, right? And you want to represent this image with an MLP, right? And you feed on the left, you're feeding just the 2D coordinates. And you're asking the MLP to train, to represent or memorize this image, right? And as you can see, if you do not use any positional encoding, it does not do a good job. Whereas if you use positional encoding, it does a much better job. So that's one of the things that made this network work. Okay. So once you have this network, right, and let's say you have lots of views, all you now do is you have rays, right? You know the camera positions first of all. That's one thing you need to know in the standard nerve setting. And you sample points along rays for every pixel that you have, and once you have sample rays, then you go through this volume rendering equation, which is completely differentiable, and then you get a color and from that ray, and you can then basically do this, what I talked about as analysis by synthesis. Compare that color, the rendered color, with the observed color from that image, and you do that for all rays from the training images that you have for that particular scene. And once you kind of optimize, you get this representation, which can now be rendered from any view, right? So these are some of the results of NERF. So you take few images of an object, and now you can render from any view after you have trained, right? So what you are seeing here mostly are like renderings from kind of novel views, right? So I think in this particular video, which is from NERF authors, the nearest input view is shown at the bottom, and on the right you can see the rendered views once you have trained that MLP, right? Any questions at this point? Right. So essentially, you have basically have gotten both a 3D reconstruction of the scene, because you have underlying, you have created this density field. So you can also render like depth images from this, right? Generating depth images is very similar to generating color images, where basically you kind of overcompensate the depth values instead of color values. So I know I gave a very fast kind of overview of NERF. I think I would highly encourage, like, you probably want to go through the talks that are associated with this paper, and they probably do a much better job in explaining this than what I did today. But in some ways, this is like an exciting work. Like when we saw this work, we're super excited. Like, we did not realize that it works so well, right? Of course, I don't know, maybe the video quality that you are seeing may not be good over Zoom. But so I would, again, highly encourage to see the actual video from YouTube, maybe. Okay, so NERF also is kind of slow. Like, it typically takes around like almost several hours to train like one scene, right? So more recently, there has been a lot of advances. Like, you can search for something called plain voxels, instant NGP, direct voxel optimization, and more recently, like ReLU fills. They're all kind of different in some ways, but the core idea is that instead of doing positional encoding and having a big MLP, they have learned feature grids. Right? So they basically do learned embeddings and a small MLP, right? So one way to do this might be like, you store features, these learned feature encodings, on some dense volumetric grid. And when you have that, you don't have to have a really big MLP to get your color. You can just use a very small MLP on top of it. And that gives a lot of speed up, right? So you should probably be also aware of this set of architecture, because I believe like most people are moving to this sort of architectures when they want to do neural radiance fills. Okay. Okay, so NERF is good, right? So on the left-hand side are some reference color images that you observe in, let's say, real world. And real world is moving, it's dynamic, right? And if you actually see on the right, I'm showing the nerf renderings of those scenes. And you probably realize that the moving objects are kind of blurry now. Also, it kind of lacks an object-aware understanding, right? You also don't know the semantic understanding of the scene. Like you don't know if this is sky, if this is road, if this is a car, and all those things. So how do we solve that, right? So how do we make nerf work for dynamic scenes? How do we incorporate an object-aware understanding of the scene? How do we incorporate semantics into the representation of the scene, right? And that's exactly what we attempt to do in our CVPR 2022 paper, which I'm going to talk about right now, which we call Panoptic neural fields. It's not just me; it's a lot of authors. Um, so let me try to give a high-level overview of what I am doing. So you can, so there is a, so given any scene, you can actually decompose a scene into this concept called stuff and things. This distinction was kind of quite common in vision literature, where by stuff you typically mean amorphous surface, maybe something like, let's say, sidewalk, sky. Um, um, Another example, maybe building facade, right? Whereas things are this kind of countable objects, like something like car that which you can count, and they typically have like a very kind of a similar concept of shapes among all categories, all instances of that category. So all cars kind of more or less look similar, right? And they're countable, right? And that's what we mean by things, right? So you can divide basically the scene into this things and this amorphous surface is called stuff, right? Um, so what we do in panoptic neural field is, for those of you, panoptic neural field, if you know what panoptic segmentation is kind of very related, right? So you want to have a segmentation for panoptic segmentation. You also have you combine basically semantic segmentation with instance segmentation, right? So here, what we do is that for every object instance, we have a nerf, separate nerf that is tied to the object's coordinate frame. Then for the stuff, we also have another nerf that represents the background static world. So these are on the right, I'm showing the results that you get when you use panoptic nerf. And as you can see, moving objects are now correctly reconstructed. You can also get a semantic understanding of both the background and the object instances, right? So the nice thing about this network is that in nerf, you created a radiance field, right? So at any 3D point, you can query the color and density. Here in our panoptic neural field, at any 3D point, you can query not just the color density, the radiance, but also the semantic and instance level at any 3D point over time. Okay. And you can actually use this for a lot of applications now, right? So you can take this neural field and you can render it from arbitrary view, and you can get semantic segmentation, you can get instance segmentation, right? You can render depth. And also, because we have this concept of objects in it, you can actually manipulate the objects. So you can do some sort of scene editing, right? You can insert new objects, you can kind of clone objects, right? So all these are possible by this single representation of the scene that can be used for multiple different applications, right? Okay, so let's look a little bit inside as to how this works, right? So as I said, the stuff is represented by a separate kind of a big MLP, which takes as input position and direction, just like NERF. But now it also outputs semantics along with RGB and density, color and density, right? So we basically add another head on top of the standard NERF MLP that produces semantics, right? Then for every object instance, we have a separate MLP that takes just the position, direction, and produces the RGB and the uh, color and the density. We also need to know what's also the pose of the object over time, right? Because this individual small MLP NERF for every object is with respect to the object coordinate frame, right? So that's kind of gives is our scene representation. So basically, we represent the scene as basically the parameters of the stuff MLP, the parameters of every object MLP, along with the track parameters, right? So you basically want to optimize all of them given some images, and that then you basically have this representation of the scene, right? Now, as I was showing before, right, like we are working on this kind of outdoor scenes where the cameras are mounted on cars, like self-driving car, for example. So you will typically not see, let's say, parked car from like 360 view, right? Like you probably saw on the NERV videos. So you typically only see the cars from one side, right? So how do we fix that? So that's like one big problem, right? But if you realize in standard NERV, you always start from scratch, right? Now, when I was talking about kind of this thing MLPs, like for object categories, one nice thing about objects is that objects of the same category are typically very similar in 3D shape and appearance. So cars, more or less, they kind of look very similar, right? That's why we actually gave them a name called car, right? Because they kind of look very similar, right? So how do we incorporate that prior, right? So one way of incorporating kind of this prior knowledge that cars kind of look similar is kind of having a shared MLP where you can have for every car instance, you have some small latent code, but the MLP parameters are shared by all instances, right? So every car now has like a specific instance specific latent code that describes what that particular car is. Now, the problem with this approach is that if you're now, let's say, training this to represent, let's say, all cars in the world, your shared MLP needs to encode the knowledge of all these cars, right? And it has to be quite big to encompass that knowledge, right? And that's bad in a sense like that MLP becomes big, so it's slow, right? So what we do instead is use instance specific MLPs. So every instance would have a separate MLP. Now that MLP only needs to represent a particular object, that particular instance. So for example, it needs to represent like a particular model of, let's say, Ferrari, right? It doesn't need to know about Maruti 800, right? So it can be very, very small, right? So when you have, let's say, lots of cars, because you have small MLPs, things can be much faster, right? But that's good, it can be fast. But how do you kind of incorporate priors? Like, because these are all separate, and if you start training from scratch, they don't even know anything about that I have seen this car before, or I have seen a car object before. So how do you incorporate that knowledge? So the way we do that is through meta learning, kind of finding a kind of better initialization and transferring that knowledge of prior through that. So on the top part of the slide right now, so think of basically if you do a naive initialization of the parameters of MLP, which is denoted by the red point, during the course of your optimization, you are moving in the space of the weights of the MLP. And then finally, you, for every object, like every car model, you are finding a point that you kind of is the hopefully the local minima, right? Basically, it best describes the set of images that you are using to train that particular object instance, right? Now, of course, if you have enough time and enough number of iterations, even if you start from any random initialization, you'll finally hopefully reach that global minima. What you try to do through this meta-learned initialization method is to find a better initialization for an object category. So what we are doing is that we are trying to find a point green which more or less looks like cars, right? So there are different ways you can do meta learning. So there is a standard method called model agnostic meta learning called MAML. What we instead do is an approximation of that, which is called federated averaging. So the algorithm is very simple. Let's say you have lots of car instances and you have some images of each of them, right? So you can train a nerve for each of the car instances separately, right? Independently, you train a nerve for each object, right? Then you get it at the end of that optimization, you get, let's say you run it for like a couple of epochs. And then for n, now let's say you have n cars, and then you get n set of MLPs, right? And you actually average the weights of the MLPs, right? And then you use those new weight, which you got by averaging, as an initialization for round 2, right? You then again start from that point, and again you optimize for, let's say, a couple of epochs. And you keep doing this process multiple times, and you will soon see that you kind of find a initialization where it already starts to look like a car, right? So the nice thing is, even if you have very small number of views, you still can actually reconstruct the car properly, like a complete reconstruction. So on the left, I'm showing some input views. So for the first 2 rows, I only have one single image that I show that I have of the car. So if you do like a standard MLP Javier initialization of your MLPs, and you do nerve training, you kind of get a result like this. So as you can see, it doesn't really look like car if you look closely. Whereas if you use the learned initialization that we just talked about, you kind of get much more realistic car, even just from one image as input, right? Of course, as you have more images, both the methods starts looking better and better. But even if you have lots of images, this learned initialization is still beneficial because it's faster. So you don't start from complete scratch. You are kind of starting from a point where it almost looks like a car. So you can converge in fewer number of iterations, even when you have lots of views. But the big advantage is when you have small number of views. And that's very important for, let's say, the data sets that we have been working on. Because as I was mentioning, So you have let's say you have a camera mounted on top of a car and it's moving on the road. You will typically see the parked cars only from one side, right? And even if you see them for a couple of views, you typically have very low parallax, like you don't see them from like 360 views or something like that. Okay. So okay, so now to do the learn initialization, you still need to see lots of images of that particular object, right? But what if you don't even have that, right? So for those, you still want to incorporate some knowledge about the scene, right? So as I was saying, like we have this concept of stuff and things, right? So stuff is mostly, let's talk about objects, right? So these objects, for example, it can be a car, it can be a pedestrian, it can be a lamppost, right? So for cars, we basically have some data, like we actually use ShapeNet. I don't know if most of you might know ShapeNet. It's like a data where you have 3D models and rendered images of the 3D model. So we use that to incorporate knowledge of cars. But for other classes, we don't have any additional data. But we basically want to say that these objects, they're mostly occupied, mostly full inside the bounding box, inside the tight bounding box of that object, right? Which is typically true. If you have a bounding box, tight bounding box around, let's say, some object, it's mostly full. But the same is not true about the stuff, the scene. Most of the space in our scene is empty, right? So we actually use that knowledge to our advantage by adding some simple bias terms. And surprisingly, that also really helps in kind of making this algorithm work. But then, of course, when you have some additional data for this particular set of categories, you want to do the learned initialization that I just described previously. Right? So that's the initialization, right? So you have these MLP parameters for the stuff and thing. That's exactly how we initialize them. Now, how do we train them? So given, let's say, some data collection, let's say I was talking about, let's say, self-driving car with some camera on top of it. So you have those images. What we first do is run some sort of SLAM algorithm, which gives you camera pose, right? So for every image, we know where is the camera is, right? Then we do some sort of object tracking. And we also run some off-the-shelf 2D single image segmentation, right? So you have all of them. Now you're basically doing what I was saying at the beginning of the talk is analysis by synthesis style loss. So you have your representation. I can render from any view the segmentation and color, and I kind of compare that with the observed color image and the predicted semantic segmentation image. And that's basically my optimization. So that's what I train for, right? Once you have trained this, right, you can, as I was saying, like render from any view, you can manipulate the objects and do lots of things. Right? So I'm going to show some results, including like manipulating the objects. So all the images that you are seeing here are all rendered images, right? So as you can see, like it looks very realistic, and you not only get color images, you can render segmentation, semantic segmentation. You can also render instance segmentation, which is shown on the bottom right, and also you can render depth images, right? And as you can see, the depth images are kind of also quite crisp and pretty good, consistent, right? This is another scene. So you will see multiple, not just cars, you have buses and pedestrians also. And also for the bus, some of the windows are transparent, so you also kind of capture that. this is another scene. I think one big challenge in this particular scenes is that um, your camera doesn't move that much, so you have very low parallax, which are kind of quite hard for reconstruction, even using traditional methods like photogrammetry, structure motion, SLAM. Uh, okay, so now I was mentioning about scene editing, right? So you have these object nodes in your representation. You can use it to manipulate, right? So on the top, what I did was basically you can replicate the parameters of the MLP for each object and make every car look same, right? Simple modification. And rather, also you can like modify the 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 pose of objects, so you can make them dance if you want, right? It is another result of scene editing. So on the left is the rendered images, but I'm not modifying the scene at all. On the right, I am basically inserting some new objects and moving them around, right? So you can do that because this representation is object aware, right? So the bus and the car, one of the car is kind of put into this scene. They don't exist actually. Okay, so let's look at some of the kind of numbers, quantitative results for this approach. So there is this, so all the results that I was showing before are done in this data set called Kitty, which is a very popular data set for autonomous driving applications. So they recently also did another new data set called Kitty 360, and it is the first data set where they actually evaluate both novel view appearance, the color images, and the semantic images, right? Uh, so as you can see, our method can do both, right? It can render color images, it can render segmentation images. And we kind of get quite good numbers. Uh, so, okay, so maybe let's focus a little bit on the novel view semantic synthesis task, right? One way to get segmentation on a novel view is like this, like you run vanilla nerf or any other nerf method that you like, generate a color image from this novel view, right? And then once you have this color image from novel view, you can run your favorite 2D semantic segmentation algorithm on top of it. And you can then have some results for novel view semantics. So as you can see on the right table, right, our method is much better than this two-step process method. So for example, all these methods, like for example, the first row is like nerf, you run nerf, and then you run an algorithm called PSPNet, which is basically a 2D segmentation method. So why is that? The reason is that you kind of incorporate all the views into this, right? And it's basically an integrated method. So you see all those benefits that we get with our representation. So here's some results on that data set. By the way, just to keep in mind, we are still using only the forward-facing cameras. So this data set does have 360 cameras, and LiDAR, we don't use them. We just use the forward cameras, right? So again, on the left, I'm showing the rendered semantic segmentation, but on top of the color images for better visualization. And on the right, I'm showing the rendered depth images, right? So as you can see, even like the thin structures like lamppost or sign symbols are both correctly segmented, right? And also you get the depth to be also perfect, right? Almost perfect, not perfect. And another nice thing is that you get temporal consistency for free, right? So what I mean by that, like for people who work on video semantic segmentation, one thing they try to do is to run, it is to kind of capture temporally consistent segmentation. And they have to have a lot of ad hoc methods on top of that, top of like single image segmentation methods to enforce that. But here you just get temporal consistency by free, just just by the way you constructed the model, because you only say the density in 3D is not conditioned on view direction or anything like that, right? Here is another example. There are some, so if you go to our website, you will probably see more examples of this data. So over Zoom, they might look kind of low frame rate. So yeah, so basically, I think that's basically kind of what our method can do. So given some images, we can build this panoptic neural field, and you can use it to render segmentation, instant segmentation, depth, color. You can modify the scene, all these things. So that kind of brings to the end of my talk. So there are two things that I wanna basically convey, right? One is, if you see neural scene representations, one might think, okay, these are only useful for generating color images. What I'm trying to also say is that they're also super useful for traditional 3D scene understanding tasks like segmentation, depth prediction, right? So, and kind of one nice thing that NERF or similar methods, volumetric rendering methods, have given us is a very excellent rendering algorithms that doesn't need silhouettes or anything. You can just use these differentiable renderers to create 3D just from images alone. So you don't need any supervision. So everything is self-supervised. So because we have these really powerful volumetric differentiable rendering engines now, which work much better than even like 3 years back, I think we are going to see computer vision being solved with much more often with analysis by synthesis style math supervision. Like basically, like you have some model, you render, and then you compare with the observed images, and that's how you update your world model parameters. So maybe even object detection, maybe optical flow, a lot of all these things may be solved in future by this kind of methods. So yeah, that's basically concludes. Feel free to reach out to me, and I'm also here to take some more questions if you have.
Hello, can you hear me? Abhijit? Am I audible?
Sorry. Yeah, I can hear you.
Okay, so we have a few questions. So thanks for the talk, by the way, and yeah, over to the audience.
Yeah, hi, Abhijit. Thanks a lot for this introduction to know. Very good introduction, actually. You have pointed out that we are passing position coding. Can you please go to that slide and tell us how we are passing position coding? And when you say that in terms of spatial coordinates, x and y, we are transforming them to a Fourier function. How does that capture high frequency components? My belief is that only just passing the x and y coordinates does not really tell model anything about the higher frequency coordinates. Or we are first applying a semantic mask over it and then creating Fourier transform. If you can go to that slide.
So I fully couldn't capture exactly what you said, but I think you were talking about positional encoding slide, right?
Right.
How
does positional encoding is passed to the model?
Okay, so positional encoding basically, so So for the input coordinates, right, x, y, z, or x, y, or x, y, z, right? So by the way, one thing to also remember is sometimes these networks are also called coordinate networks, coordinate MLPs, right? So you are passing some locations like x, y, z, and you can use that coordinate and use some Fourier features. They can range from different set of frequencies, right? You can have like higher frequencies, you can have lower frequencies, and you basically get now, instead of 3 vector like x, y, z, let's say depending on the number of features, you get a kind of longer dimensional feature. Like, I don't know, depends on the number of frequencies you use, maybe something like 30 dimensional feature, right? You do the same with directions, and you use that feature as an input to the MLP, right? So the only change that we do in panoptic neural field, so for the stuff MLP, what we have is just like you have a head, one fully connected layer that predicts the density. We have another fully connected layer that predicts the semantic logics, right? So the output of this particular fully connected layer is 1, whereas the output of the semantic logic fully connected layer is a number of categories, right? And just like here, it's not the direction does not go into the semantics head, which basically says that the semantic at any point is not dependent on view direction, right? Color is, right? With so if a, so any 3D point is belongs to one particular category, right? It doesn't change depending on how you view it. So that's the inductive bias that is incorporated there. I don't know if I answered your question, but
Yeah, I got the idea, but my question was around how does passing special coordinates, isn't it when we pass them through Fourier transform, we're just saying that a particular color or a particular pixel is appearing multiple times. So basically a mapping of particular pixel coordinates. So we are, how does spatial coordinates encode the high frequency component information?
So I mean, so it's not like so the high frequency component is not encoded by just the like the positional encoded features, right? What you want to give to the network is set of feature vectors that varies both slowly and kind of in a fast way at a high frequency, right? So it's not just that like the spatial coordinates have to encode the high frequency components there. The MLP will be incorporating the high frequency components that you see in the color and everything. It just basically makes the training of the MLP better. Like without those encoding, positional encoding, you would not be able to get good results. So I would suggest like the paper that I have linked there is a theoretical study of, not theoretical, at least they give some theoretical explanation which kind of uses the idea of neural tangent kernels to explain why some of this thing works so well, right? Another alternative, which I probably also mentioned, is instead of just the small set of coordinates, like 3 parameters, you can have a larger vector, let's say 64 dimensional. and you don't need positional encoding. So in some ways, positional encoding is just like some functions that you probably give that has some nice properties. But what you're doing here is like you are asking the network to learn a better embeddings, better encodings.
So thanks, Abhijit, for the talk. I have a question. Like, why was not able to capture the objects in its images by synthesis? It should have been able to capture the moving objects like cars. So, what limited not to capture such moving objects because of which you started with the instance level stuff and things. So why was not able to capture the objects?
Okay, so is the question, if I understand you correctly, you're saying why NERF was not able to capture the moving objects in first place?
Yes.
Okay, yeah, that's a good question. So let's look at how NERF does this training, right? So what NERF assumes is that so let's say you have some colored image. Let's say in this case you have two colored images, two views of the 3D world, right? And you sample points along rays for every pixel, right? And you also sample and so some 3D points would project to both these images, right? Now, if this object is moving, right, then what happens is that that consistency is no longer there, right? So that's basically what kind of prevents it from properly capturing moving objects. So what happens is that like here, if you see, I don't know how much is captured. Like it basically blurs, kind of becomes the moving objects becomes kind of blurry trails, right? So the whole model of NERF basically relies on the fact that it's a static world assumption. So every 3D point, the density is fixed, so that when you project them from different views, they should be consistent. So that's basically the underlying assumption of kind of vanilla NERF. You sometimes, for example, I don't know if you can see in the second image, you will see some dynamic effects being there. And so that can come from little bit of the view direction effects that NERF has, right? So you can probably kind of cheat by putting the dynamics in the view direction, but still it's not it cannot solve dynamic scenes.
Thank you. Thanks, sir. So my question is regarding the Panoptic neural feed. So does that method also work if the camera is also moving and the scene or the object is also moving? So if the both things, like the object and the camera, are simultaneously moving, does this method still work?
Yeah, it is actually. Yeah, I mean, we don't have any restrictions on the camera movement or anything. So if you see here, the camera is actually moving. For all these scenes, the cameras are kind of parked or are mounted on a moving car. Though some of these results that I was showing, they were like very small clips. But I think, yeah, for example, yeah, for example, this result, you will see actually the camera, the original camera views that we use for training were basically like the car is moving forward, similar to this. Also, I think even this one also, the car moves and then turns left. So it should be the whether the so it can represent both like kind of moving cars, and it can also do handle camera car motion. But of course, like if you just have like one view of an image or a very small number of views, it becomes harder to reconstruct the stuff background, right? Uh, because for background, if you remember, we are not doing that kind of prior or anything. But for cars, even from like one or two views, you can still get a good sense of how the 3D looks like because we use the prior that I mentioned.
I just ask because in this the one that you are showing right now, it appears that
Yeah.
the camera is moving, but the scene is static. I mean, the cars and everything is static. So my question came from that perspective. But
Yes. So yeah, so this scene is from Kitty 360, where basically they only selected static scenes. But let's see. I don't know if you can see this one well. I think the car camera also kind of moves. Um, I don't know if you can see that. Like it's a small movement, but it actually moves and stops because of the red light.
Hello. If you can go to your last slide where you showed NERF and other methods are not just for novel view synthesis, but also for 3D scene understanding. So, like, is it really solving the problem of 3D reconstruction from the geometric point of view? Because when we see the results, it's usually in the form of the images, like the rendered images from NERF and like the original images. So, if we consider medical applications where the geometry needs to be very accurate. So, like, is it really good in that way also?
That's a good question. Like we have not done a thorough evaluation of how accurate the geometry is. Like for semantics, for color, we have an evaluation because it's easier to do because you can measure something like because the color images you have, and then there is also some ground truth that we have in terms of images for segmentation. For 3D, it's typically a harder thing to do because you typically don't have ground truth. And we really need to do that. So that is something that we have not done in this much work. But I would say like kind of visually looking at things. And by the way, one thing, I don't know if you can see the beginning of the video, these views that I'm showing are not like in the wild different views from the input images. But if you probably saw at the beginning, I'm kind of doing like a little bit starting from much higher vantage point and then coming down, right? So it's kind of quite novel in that sense. So at least the views which are kind of close by to the original camera path, you typically get pretty good depth. So I would also ask you to see papers like Urban Radiance Field from one of our colleagues. They explicitly get a mesh out of the nerve. They are starting to look pretty good. What I would say, even also there was like a paper, neural 3D reconstruction in the wild. I think it came out yesterday or maybe the day before yesterday. If you see those results, they are already starting to kind of beat traditional photogrammetry results, at least or they're challenging them. And I believe in like give it like another 1 year. I'm pretty confident that methods that are based on neural scene representations, volumetric rendering, are going to be the state-of-the-art methods, even for reconstruction, not just view synthesis.
Okay, great. One last question. Hello, am I audible?
Hey,
Yeah, so my question was regarding you do this meta learning thing, right? So you do it for each kind of class. So you do it for all cars, maybe, and maybe buses. But what happens if you on the road you see something that you have not learned on? Like suppose you see a bike, you take the same model and you run it in India, you see bikes and autos. So how does it react to that kind of thing?
yeah, so exactly. So I was mentioning it here that if you have, let's say, you are seeing a bike cycle and you don't have a corpus for cycles, what you would do is that you still use this what we call as bias initialization. You still want to basically want to say that most of the volume inside the bounding box of that bike is mostly occupied. So you can still use that knowledge by just simply changing the bias initialization values when you are training. But of course, if you know if it's a car or you have some corpus of car, you can probably use that.
Okay, really great. Just one last point, like you have mentioned in your paper, that's computationally heavy, but and offline. But how much computation do you think an academic group like us can try to train your model on Indian roads and do something, or it's just Google can do that or Facebook can do that?
Well, yeah, I think with the current, what I would say, the backbone that we have, which is kind of traditional nerve, I think it is very, very hard to do it outside of Google because it takes a lot of times. Like if you have just GPUs, it takes several hours if you have just single GPU. But as I was mentioning, the instant NGP, Planox cells, ReLU fields, if you change the nerve backbone to those kind of things, it becomes much more practical.
Okay.
And it is easily doable. It's not hard.
Yeah, no, I mean, we have a big cluster, I think more than 16 GPU machines with each 2080 Ti, I think, at Reply T. But question was more like, for example, a video you are taking and you have a, let's say, 4 GPUs of 2080 Ti for you for one day, will that easily scale up? And within a day it will be done, or you need more advanced hardware?
For 4 GPUs, yeah, you typically you could take no, like depends on the scene, but it would take couple of hours still
Oh, that's great.
for
So-
one scene.
So do release the
With
code. Do release the code there.
yeah, so yeah, we are working towards that. It's a little bit of a slow process here, but we'll see.
That's really great. Thank you, Abhijit, for interesting talk and SOTA results, I think, sharing with us. Yeah, I mean, it was really great. In fact, today I just felt nostalgic. I was searching your email for sending something, and then I just saw the 2008 email that you sent me in July. You know, and it's like you have really reached to places after that, and I'm really happy that I also played a minimal role in connecting you with Samano. Really great, yeah, listening to you, and I just sent you as a token of you participated in this talk and helped us conducting this event. So just sent a Amazon e-gift card. So I hope you'll make use of that. And thanks a lot for joining remotely, and we look forward whenever you visit India, you can feel free to visit in person, and then we can definitely find. And we are very interested in articulated objects, reconstructing them, and learning generalized nerve, so those kind of things, or something like dance structure and other kind of stuff. So, okay, thank you. Thanks for joining.
Thanks a lot. Thanks a lot for inviting me. Yeah.
Bye bye.
Right.
So we have some time and we just thought this around half an hour or more. Dr. Charu can talk about her CVPR paper, right? Or in general, okay, what